Hello, physical geology students. It is time to learn about volcanoes a bit. So this week we're going to talk about volcanoes. Another week we'll talk about igneous materials that, in terms of their chemistry and so forth. But volcanoes are kind of the most physical, the most recognizable manifestation of igneous petrogenesis. But really, I mean, when we talk about igneous rocks, I mean, they are the most primordial rocks out there. When the Earth began to cool from its molten state, igneous rocks were the first things created from those melts in the early during the early Earth. So, of course, volcanoes came along later. You had to have solid Earth, solid plates for them to occur, and then eventually plate boundaries and so on and so forth. But it's so there's the volcanoes have been around since just about the start of the Earth's history, and it's important to keep that in mind. But they've of course been evolving since then, just like the igneous materials that come out of them or that produce them and then come out of them, I should say. They aren't the same today as they were then. They're chemically that their chemistry has been evolving over time as well. But let's get into this a little bit. We're going to look at molten rock. We're going to look at associated hazards and the different types of volcanoes that are produced based on plate boundaries. So this is kind of picking up from our discussion of plate tectonics and then our discussion of rock deformation. And then we'll get into this, and then we'll get into the other related materials. First of all, again, some of this is going to be review. Maybe you had earth science in ninth grade or eighth grade, or maybe you've heard a lot of these words before. But molten rock comes in two forms. If it's still intrusive or inside below the surface, we call it magma. If it has extruded onto the surface, we call it lava. And lava can come in a variety of forms. Two major forms that or names we actually give to lava flows are Pahoehoe and A'a, and they have very different characters. This is the Pahoehoe flow on Hawaii. And of course, anytime you're talking about magma and it cooling into a rock, you're actually talking about it freezing. And that freezing can be rapid or slow. And that speed of um, the speed of that cooling determines the texture of that rock eventually. So it can either be glassy and really fine grained or really coarse grained, where it cools really fast, or really coarse grained phaneritic, which is the term we use for that, or even have two cooling phases, um, where it'll be very slow cooling under a regime of very slow cooling in the ground, usually in that case. So anyway, so lava and magma, it's the same material. We just give it different names depending on where it is. So last year, you may have heard about the Mount Kilauea in Hawaii erupting, and of course, Mountain Hawaii, the big island of Hawaii, has several volcanoes on it. Kilauea is just one of the most active. So Hawaii itself is a string of islands made up of nothing but volcanoes. Most of which are extinct now, because many of them continue on past Kauai and on into the Emperor Seamount chain, and so or have stopped erupting, so they're now below the surface of the ocean. But Kilauea is one of the youngest of the islands, and not the youngest, but one of the youngest, and it still produces a really great show. It's not a terribly violent eruption in the sense that it's not like a Vesuvius or Mount St. Helens or a Yellowstone, but it is an eruption that produces a lot of the textbook kind of stuff that we associate with volcanic eruptions. So here, for instance, big lava flows. Here's a great example of a lava flow, kind of bordering on the A'a kind of flow, where it's kind of began to cool. It's much blockier. It kind of rolls over on itself rather than just flows. And clearly, they're going to have to do some road work after this. But you can see where the hazard zones are in Hawaii in terms of lava danger zones. Of course, the yellow areas are the extreme high hazards, and that's because there's a rift zone through here and so forth. And so depending on the geography, there's more hazards in some places than others. Now, these volcanoes on Hawaii are shield volcanoes. We'll get to those in a second. And because the lava just sort of flows out over the surface, you get lava tubes also under the surface where lava is flowing um, various places. And this is very characteristic of shield volcanoes to have these kinds of flows. Not a lot of ash, but a lot of lava. And some of those tubes, of course, the lava is flowing underground and overground. And some of those tubes cool off, and then they become lava caves. and those are a lot of fun. I actually had a chance to go in some in Mount Suswa in the East African Rift Valley. Our friend of mine who's Kenyan took us there. It was very close to where he grew up, and the lava tubes are just fantastic to go walking through. And of course, Suswa is also a shield volcano in the Rift Valley, which is a divergent boundary where you would get shield volcanoes also. So, all right, here's another example of a typical eruptive feature of Kilauea: fire fountains. So this is out of a fissure eruption. So the crater itself in Kilauea will have eruptions, but they'll also be radiating out from in various places fissures that open up. Now, sometimes these could be lava tubes that are under pressure, and the surface breaks, and you get fissures of lava erupting out. But it's very dramatic, of course, and of course, the texture of that is very different than the flowing lava. Another great shot of lava causing damage all over the place. Of course, there's one housing development in particular, Leilani Estates, that was most affected by these flows this past year. This is 2018, referring to, and it was right in one of those high danger zones for lava, which is the East Rift Zone. You'll remember that there was also one right through here, but the East Rift Zone here is, of course, one of those high danger zones. And you can see where there's different lava flows from different eruptions back in 55 and 60 and 1840 and so forth. And they built some housing developments right on top of where lava's been. Leilani was over here, and so the eruption, of course, produced lava that flowed all over the place. Some of this lava, the Pahoehoe flows, were traveling at really high rates of speed, really high velocities at times, depending on where they were. But Hawaii's not it. There's volcanoes at least as far as American volcanoes go, United States volcanoes, not including anything in British Columbia, not including anything else in the Pacific Ring of Fire. But there's a lot of volcanoes in Alaska, as you can see, and then along the west coast of the U.S., and even further inland within the Rocky Mountains, and of course Yellowstone. There are extinct volcanoes here in Virginia, but we don't mark those because they're extinct. So Mole Hill, Trimble Knob, and then various intrusive features we call dikes are also all over the place. There's ancient volcanoes up through New England from the Acadian and Taconian orogenies, where we had mountain belts that had where there was volcanism going on along the east coast or along an island arc that was accreting during the Taconian period back in the Ordovician. So anyway, Kilauea and associated volcanoes are not the only ones here in the United States. And of course, volcanoes occur actually at nearly any kind of rift valley, less so along transform faults, but because they do occur all along divergent boundaries, you do get them near transform faults. But mostly divergent boundaries, hotspot, which are mantle plumes upwelling from deep within the earth, but that are stationary, and then of course partial melting of the upper mantle. Not this is important here. When the piece of lithosphere here is subducting, it's not the thing melting producing the magma. It's actually the upper mantle, because what's happening is you're bringing in all these extra sediments, but you're also bringing in water. So you're hydrating the upper mantle, which moves the solidus. And we'll get to that in a second. But this produces continental volcanic arcs like the Cascades. So depending on your plate tectonic situation, you're more than likely going to be able to find volcanoes associated with it. All right. So in summary, we have volcanoes in island arcs, which is like a Japan type situation. So Mount Unzen, Sakurajima, and so forth are examples of that. And then mountains along the mid-ocean ridge that are volcanic, as well as hotspots like Hawaii and so forth. And then the Cascade type volcanism, or Andes volcanism, or Sierra Nevada volcanism. A variety of other possibilities there. And of course, volcanoes all around the world. You'll note that not all these, you see these toothed lines are subduction zones. The teeth are on the overriding plate. So the Asia is overriding, or actually should say the Pacific plate is subducting beneath all these other plates. And you'll see these are divergent boundaries, and there's volcanoes along these really all over the place. But East Africa as well, volcanoes. But so even out here in the Mount Pelée and Martinique and so forth are great places for volcanoes as well. Now, of course, as you all know, as you go deeper within the Earth, it gets hotter. That's called the geothermal gradient, and that's what we're looking at here. But the geothermal gradient doesn't behave the same way at every single plate boundary. So if you're in the middle of the continent, it's going to behave in a normal situation. So in the middle of the oceanic lithosphere or in the middle of the continental lithosphere, you're gonna it's gonna keep going, getting warmer as you go deeper within the Earth. Here's depth versus temperature. Eventually, you might reach the solidus eventually once you reach the lower part of the upper mantle. But really, in order to get to that point, you need to increase temperatures rapidly without going very deep. And that's a great place to do that as a mid-ocean ridge because the lithosphere is very thin there. And so the temperatures increase very rapidly and you get molten rock, which is why we have molten rock there and why we're producing lithosphere. Another situation is this, of course, a little deeper where you get these mantle plumes upwelling that produce these hot spots. But again, at a certain depth, somewhere around 80 or 90 or 100 kilometers, you do cross the solidus and you're able to produce molten material that's able to buoyantly move up through the lithosphere. And then finally, now this is the interesting place right here. When you're subducting, again, you're bringing water down with you, so you're hydrating the upper mantle. And when you do that, you see this green line hasn't moved this entire time we've talked about it. That's the solidus. Molten rock here, solid rock here. Whenever the geotherm crosses the solidus, you're crossing into melting the rock. Well, look what happens here when you add water to it. So when you add water, you hydrate the rock, it melts at a much lower temperature. So a normal geotherm can experience a lot of melting at certain depths, and anywhere down. Of course, this is along the Benioff zone down here. So you're still getting earthquakes and stuff, but you're also now getting volcanism. But again, it's the upper mantle that's melting, not the subducting lithosphere. Okay, so depending on the tectonic situation, whether it's divergent, convergent, so forth, you're going to have different magma chemistries. Because if you look at this, you're having, in this case, you have mantle material coming from deep within the Earth, and again, mantle material coming from deep within the Earth. That's going to be very, very mafic, very low in silica. Contrast that with over here. Now, this is oceanic lithosphere, so you're going to produce an intermediate or andesitic situation here. If this were continental lithosphere, you'd be producing andesitic or intermediate, but you also be producing felsic because the silica content's that much higher. Because remember, continental lithosphere is primarily granite, higher in silica. Oceanic lithosphere is primarily mafic rocks or basalt, much, much lower in silica. And so the silica content is very important. The more silica there is in the magma, the more explosive it is because the silica allows the magma to retain a whole lot more volatile gases, including water vapor, which is the number one gas that leads to explosive eruptions. Hence, the water vapor specifically pulled out as a major component here. Just note down here at 50% silica, the eruption temperatures are much higher. So, we'll get to, when we talk about igneous rocks, we'll talk about how that works. But the certain minerals like olivine, you have to have much higher temperature to melt them. So if you're going to have mafic magmas that contain a lot of the really iron and magnesium rich minerals, you're going to have very hot molten rock. It's not as hot over here. I mean, it doesn't take as much to melt a granite as it does to melt a basalt. So the gas content is a good 10 times higher here than it is over here with basaltic magma. And then so it's much more explosive. What this ends up doing is the magma ends up being very thick, very viscous. And you end up with really a lot of pyroclastic deposits, a lot of really, basically the mountain blows up, and you're talking about mountains that are on the continent. So you get a lot of big lava domes, a lot of pyroclastic deposits, a lot of broken rock and ash, things like that. Whereas over here, you get mostly lava flows. So your different types of volcanoes show up in different locations based on the silica content. And that's important. Silica content, volatile content, temperature leads to more or less explosive and the type of volcano you get. But here's another summary. I would pause here and just study this for a little while. This is a really good summary. It's in your textbook as well, but it does a good job of checking that out. I would also go back and study this for a while. These are two great diagrams that are worth spending some time on. Okay, Now, magmas do intrude into a chamber of sorts, but they're not. Those chambers aren't just big holes in the ground, and they aren't just a simple, single chemistry magma that sits in those chambers. There's usually a stratification of different chemistries within a magma chamber. It's a pretty complex place, and it then, of course, produces a complex suite of eruptive or intrusive products. But depending on the chemistry, especially in a situation like this where you have the upper mantle of the continental lithosphere melting, you have sediments that are perhaps melting along with that in the water. That affects the chemistry of the rock that you're getting. You're going to be getting some intermediate volcanics as well as eventually some felsic volcanics and some very explosive volcanoes. Within the magma chambers themselves, these areas here, you'll have some mafic magma, but you'll also have intermediate and felsic magmas as well, and chunks of the country rock, which is, we say country rock again, it's just that rock that's surrounding the area. So Kilauea lava looks a lot like this. You have primarily basalt, that's what this says over here, which is again very low in sodium and potassium, very low in silica. So that's important to point out. Contrast that with Yellowstone. Contrast that with Yellowstone lava, which is very rhyolitic in composition, very rich in potassium, it's very high in silica. If you look at Mount St. Helens, which is again, now we're looking again at a continental volcanic arc in the Cascades, where you're getting everything. So we go back to this slide, you see you're getting all of these pieces in here. So there's, depending on the time and situation, you're going to have some mafic intrusions, you're going to have some felsic materials that are really explosive, and some intermediate materials. You can see how the chemistry ranges all the way from basalt to rhyolite in Mount St. Helens eruptions. Then you look at a place like Vesuvius. Vesuvius is a part of a volcanic arc that is, of course, in Italy, and it's separate from the volcanics that are making up Sicily. So we'll talk about Etna in the VFE here this week, but it's part of a different volcanic arc, but it's still a part of it's producing the peninsula of Italy is what it's doing, is the subduction area, that zone that's producing that. But the chemistries are very different, and that's because you have a lot of other things mixed in there. So there's trachytes and phonolites and things like that that are not your typical igneous rocks that like we'll look at. Now we will look at some of these because the rift zone in East Africa is like this, and I brought a lot of rocks back from East Africa when I went last year. So we'll see some trachytes and some phonolites and things that are a little less traditional than your typical igneous materials that we'll look at in lab next time. Okay, shield volcanoes. Shield volcanoes are the first type of volcano we'll mention here. They tend to be very broad, gently sloping, very broad. And they're very large, very, very large. So you can see the base can be tens to hundreds of square kilometers in terms of its coverage, 5 to 10 degree slopes, basaltic magma chamber, pretty straightforward, mostly made up of lava flows. Here's an example of a shield volcano. I believe this is Mauna Loa in the distance in Hawaii. You'll get little cinder cones on top of these where eruptions occur, as well as fissures where eruptions occur. And then, of course, the lava flows themselves. And so you don't just have necessarily a single eruptive center. You'll have eruptions occurring all over the mountain in various ways. Here's an example again of of Kilauea erupting in this case. And here's an example of Mount Suswa. I've mentioned it before, and one of its lava, one of the openings of the lava tube there. This is Suswa from space, but again, it's very broad, multiple complex crater system, and so forth. Stratovolcanoes are much steeper. Now, this is really exaggerated, but then this is from your textbook. And if you want to know what all these different things are, you got little feeder dikes, you've got the volcanic conduit itself or neck, and then you've got some fissure eruptions here, and then of course the vent itself. Then you can go to the textbook and it'll walk you through all of these. But you can see there's also a layering to these lava flows and ash deposits and so forth. So here's an example of a stratovolcano. You can see the shape of the stratovolcano is very different, very, very steep sides, and so forth. This is Mount St. Helens. Actually, this is, um, yeah, I believe that's Mount St. Helens before. This is Mount St. Helens after. This is Mount St. Helens blowing its side out back in 1980, and you can see what happens during that particular eruption. You get a lot of ash, a lot of ash. The only lava is right there in the center, and this is the lava dome here. Not a lot of lava, but you can see how the top of the mountain, when it blew off, it lost a good couple of thousand feet, which is a lot. One that's near and dear to my heart because my wife and I essentially met here. I started our relationship here. This is the island of Santorini in Greece. Here's the volcanic crater itself. The last time this one erupted significantly was during the Minoan civilization in about 1600 BC, plus or minus. And that was, of course, that was enough to potentially be one of the drivers for the end of the Minoan civilization. But again, this is an island off the coast of the mainland of that civilization, which was on Crete. But there was a city called Akrotiri that's buried in ash. They've been excavating for many, many years. There's an island here in the center called Nea Kameni and Pelea Kameni, which you can take boat rides to. This is what the island looks like today, and of course, you can see the layering of ash and so forth on the outside. And you can see just how beautiful it is in terms of the civilization that's there. And there's cinder cones and volcanic fields in general, which are again a result typically of any kind of volcanism. Cinder cones can show up within shield volcanoes, and they can show up in subduction zone areas as well. So you can pause here and study the dynamics or the anatomy here. But this is an example of a cinder cone. This is with I believe this is Mount Lawson area. So that's a cinder cone as a part of a much larger volcanic complex here. Calderas, also known as this type of caldera is called actually a supervolcano, and that's Yellowstone National Park. Yellowstone has not erupted for the last 300,000 years. And when it does, it will cause major, major problems for the whole world, not just North America, but especially North America. But more than likely not in our lifetimes, but it won't be a pretty day when it does. It's erupted a number of times. We think it's fed by a hot spot, but there may also be other explanations. Now, I read recently about how it may actually be the result of a chunk of the Pharaon plate that's lying beneath of it. And so that's a possibility as well. So it's worth keeping these things in mind. We still have a lot to learn about how the eruptive character and the geology of these different features. The Yellowstone caldera looks a lot like this. So let's say it is a rising manta basaltic magma plume, and that moves through the continental lithosphere, which adds a felsic component, of course. And then you've got freshwater and brine, which actually hydrate the rock quite a bit and end up leading to much more explosive eruptions, very explosive eruptions. Eventually, of course, it's caldera, so it will collapse into the magma chamber once it empties out, but it will cause a major eruption before that happens. You can see how big this is. The caldera itself, or the magma chamber reservoirs itself, are down here. I was watching a documentary the other day, and it was talking about how the magma reservoir is about 10% magma, and they look for 50% magma before it's ready to erupt, which is an interesting way of looking at it. But it's not an eruptive situation at the moment by that metric. But this is how some of these caldera eruptions are also actually the Yellowstone superplume. Supervolcano is associated with the Columbia River flood basalts as well. These mantle plumes will just sit here under the lithosphere, and eventually components of them will move up through the lithosphere, melt their way through, and you'll end up with flood basalt provinces. And of course, because of the hydrothermal fluids and the other parts of the aspects of the crust, there's a lot going on. You get very explosive eruptions sometimes, but with flood basalt provinces, you do get some explosive eruptions, but it's mostly just salt just flowing out. We don't necessarily have any, the traditional flood basalt provinces like existed in India or Siberia. There's nothing like that going on the Earth right now. There are smaller scale versions of that places like Iceland, where you create these big volcanic plateaus as a result of big mantle plumes. Here's the Yellowstone. Yellowstone, of course, starting out down, or actually further west than this. These are dates. So this is 16 million years ago, and so forth. 600,000 to 2.1 million years ago, and so on. This is Lake Toba. Toba was often associated with an eruption that some scientists for a while had believed had nearly knocked out the entire human race, with about 10,000 individuals left. Well, 3 to 10,000. Whether that's the case or not is still debated among scientists. But it was a massive eruption when it occurred. So these supervolcanoes are nothing to take lightly, and there are a number of them around the world. So I just pointed out two, Yellowstone and Toba, but there are many others. Here's an example of Toba again. So this is just for fun because it made me think of that. I believe, what is it? I forget which episode it starts. It's the third Star Wars, technically, where Darth Vader is essentially created. But it happens on that planet. I feel like they're in the midst of a flood basalt province, and of course they would not actually be able to standing where they are. But it makes for great movie. But this is supposed to say flood basalt eruptions. And you can see between mass extinction and the ages of flood basalt, there's actually some interesting correlation. So mass extinction in the Earth's history, and you're going to talk about this in your discussion post this week, are certain of them, and most of the big ones have been associated with flood basalt provinces. So that's, it's not necessary to say that was the only thing that caused the extinction, but certainly was a component of it. Examples of these flood basalt provinces are, many of them are right through here. There's also one, or the Camp Progress, which is the Camp one, which is over here in the Mid-Atlantic, the Central Atlantic Magmatic Province, which is associated with one of the mass extinctions as well. But there's a bunch of these all over the world, so it's worth keeping these in mind. That this is one style of volcanism that you don't hear about much, but when these things do erupt, big things happen. The Columbia River flood basalts, again, you'll see these in your VFE as well again, and you can see the layering that have occurred, just them flowing flat out onto the surface. And then, of course, different swarms of eruptive materials. Again, a giant mantle plume. These are the Deccan traps, and these erupted at the end of the Cretaceous period and are associated with the dinosaur extinction. It's thought now that by some that this was the actual major driver of the extinction. The extinction was occurring, and that the asteroid was essentially the straw that broke the camel's back. But this mantle plume was really, really big, what we call a large igneous province or lip, and so it's really it takes a super plume to a new level when you think about it covering that much of an area. You're talking about a really massive amount of magma. All right, here's an example. Here's a picture. It's not the greatest picture, but you see the Deccan traps again, flat-lying lava flows out over the surface. The Siberian traps are associated with the Permo-Triassic extinction, 250 million years ago, roughly, and you can see how big they were. So again, another large igneous province with that erupting. These things when they erupt, they're erupting for thousands to hundreds of thousands of years. I mean, just continually erupting, and perhaps a couple million years. I have to go back and look at dates to be certain about that, but they last a very long time, and it's very very significant continual eruption. Here's some other examples of these large igneous provinces, some of which are mafic, some of which are silicic, all around the world. You can stop here, pause here, and take a look at these. Now in Virginia, we also have volcanoes, primarily Eocene volcanoes, which are about 35 to 40 million years old. But there are, of course, volcanics that go back much further than that, back to the Allegheny orogeny, about 248 million years ago. But of course, the character of those different products are much different. So the Acadian material, the Allegheny materials are much more felsic, and are mainly consist of dikes, intrusive dikes that have somehow managed to make it that far. There aren't a lot of those around. Most of the materials are mafic. Now these are some columnar basalt cooling, a good example of cooling of magma. Columnar basalt, these hexagonal prisms that form are characteristic of that. things like Giant Causeway in Ireland and so forth, Devil's Tower. But these are up on Limberlost Trail in Shenandoah National Park. Then there's Mole Hill, which is the remnant of a volcano of some sort, just west of Harrisonburg. Then there are a variety of other provinces as well. That
Daddy, I'm not having time.
There are a lot of other places in Highland County and others where you see dike swarms all over the place, including Trimble Knob, which is another volcano, and so forth. Hazards include ash, of course. Here's a great example of volcanic ash. And of course, in the midst of a lahar as well. And then, of course, when we talk about volcanic eruptions, another volcanic eruption that occurred last year was in Guatemala, and Volcan de Fuego, which occurred back in June, actually was quite damaging to a lot of different people, to a lot of people and their livelihoods. Very very nasty eruption. Some of these hazards include, of course, bombs and pyroclastic flows. As you watch the documentary, I have you watching. You'll see all of these discussed. So it's really important to pay attention to that. Ashfall, volcanic poisonous gases of various kinds, sulfur dioxides and whatnot. But lahars and pyroclastic flows and bombs and so forth are probably the most prominent eruptive. Here's some fissure eruptions occurring along the side of this particular volcano. So you can see what happens with the earth. The earth tends to settle in, and you'll see fissures open up. This is a video. I won't play it here. You can find it in the notes and play it. But this is a pyroclastic flow from Mount Unzen, Japan, and this guy is driving away from it. Fortunately, he survives, but it's a pretty frightening thing to see. Lahars or mud flows also come down the mountain and at a very high rates of speed. Very dangerous. You can see there's a bridge buried by one of these lahars. Here's an example of one of these that's covered up essentially most of a little village in the Philippines from the eruption of Pinatubo. Other hazards include bombs, of course, and ash. Some of these bombs can be as big as houses and so forth, just big chunks of the mountain essentially flying out. Sometimes they're big chunks of lava that cool. And of course, certain places have had have really great stories of eruptions. Great in the sense that they are great stories to tell about the dangers of volcanism. But here's some people who were buried, of course, at Pompeii. It was really interesting that the archaeologist who first started working at Pompeii had the idea of injecting plaster into these cavities. When he did that, they did that, of course, and then once they excavated, they found that they were actually body cavities. This is at Herculaneum. You can see Herculaneum, they actually had to excavate out of the lava. It's on the other side of Vesuvius. So on one side you have Pompeii buried by ash, and the other side Herculaneum buried by lava. And here is the lava that they've excavated out, so that all that was covered. Here's another view of the same thing, Herculaneum again. These were completely gone. I mean, nobody even knew. If you read Pliny's account of the eruption, which is quite frightening to read, actually, and people talking about putting their pillows over their heads, running away from. It's pitch black. They're running away from incandescent material falling all over them. As the pyroclastic flows surround, approach, and the Vesuvius is erupting. Afterwards, nobody had any idea where these cities were anymore. And of course, you can watch this great animation of the eruption of Vesuvius over Pompeii if you go to the actual notes. I won't do it right now, but. And of course, volcanoes aren't just on Earth. Here's a picture of an eruption on Triton, which is one of Neptune's moons. So certainly other bodies erupt because of sometimes because of the tidal forces of the planet they're orbiting. The natural satellite has the volcanoes, or the planet itself, which is still cooling on the inside, has volcanism occurring. So here's a volcano on, I don't know if this is Ishtar Terra on Venus, but it's a volcano on Venus. Here's a volcano on Mars, Olympus Mons, the largest volcano in the solar system, and the volcanoes on the moon Io. Jupiter's moon Io. Now, Io, of course, has a very elliptical orbit. Jupiter is squeezing and letting go and squeezing and letting go. And that's the main source of volcanism on Io. We're going to leave it there. So we'll talk more about these in lab. And, of course, take your virtual field experience and enjoy.